Let's talk about conservation of mass for an incompressible fluid in steady state flow. I have here a pipe of varying diameter carrying water to the right, and we see a few streamlines indicated here for that steady state flow. And picture the water passing through gate 1 here to enter this region that I've shaded blue. Then that same water will later pass out of that region through gate 2 and then later on pass through gate 3 on its way off to the right. I want to look at the flow rate at gate 1, Q1, and compare it to the flow rate at gate 2, Q2 here. The flow rate is the product of the cross-sectional area at that gate times the speed of the fluid passing through that gate. So the rate at which fluid enters the blue region, Q1, compare that to the rate at which fluid is leaving the blue region over here, Q2, which is the product of this bigger cross-sectional area times the speed at that location. How do these rates relate to each other? Imagine that, let's see, this blue region is, say, a house where gate 1 is the front door and gate 2 is the back door. And there's a party going on at this house. So every hour, 10 people enter the front door throughout the course of a night. 10 people per hour entering through the front door. But suppose only 2 people per hour are leaving out the back door. And so over the course of the night, if every hour 10 people enter through the front, but only 2 people leave out the back, then we're getting a net increase of 8 people per hour inside the house. That house is getting more and more crowded over time. You would be packing more and more people into that same volume. So connecting back to our water in the pipe here, that would mean that if the flow rate here at gate 1, if the cubic meters per second, the gallons per second of water passing through gate 1 did not match the flow rate at gate 2, if there were more gallons per second coming in than gallons per second coming out, then you would be building up a greater and greater volume of water inside that zone. But we're supposing our fluid is incompressible. You cannot pack more water into that same volume. So we have to conclude that the rate Q1 and the rate Q2 must match. The liters per second, the cubic meters per second entering that region has to match the cubic meters per second leaving that region. And that will hold true at gate 3 as well. And so that leads us to what we call the continuity equation, that the rate of flow through all the gates, any gate you can imagine in some pipe, they all have to be the same. And so then we can say that the product of cross-sectional area times speed must be the same at every possible gate. So A1 V1 equals A2 V2, and that'll equal A3 V3, etc. And this enables us to relate the cross-sectional area of the pipe to the expected speed of the water or the fluid flowing through that particular section. So then here we must conclude that where the gate is bigger, here at gate 2, bigger than gate 1, since the area is bigger, the speed must be lower to compensate. And you can picture this on a bigger scale, like imagining instead of this is a pipe carrying water, that this is, say, a river. And you've got a river carrying water here that then opens up into a wider lake. And picture how the water moving fast through the river then slows down as it widens into this lake. You might not notice the flow of water at all in the lake. As the area went up, the speed went down. But then suppose there's an outlet stream on the other side of the lake, which is much more narrower than the lake itself. So with that small cross-sectional area, we have to have a much greater speed so that the rate of water entering the lake matches the rate of water leaving the lake, so that the level of water in the lake stays the same. That's a steady state flow with incompressible fluid. Here's another example of that sort of thing that you may have noticed yourself. Look at the water coming out of a faucet, the stream of water, and if you can get a nice laminar flow here, a nice steady, smooth, glass-like stream of water coming out, then we know as the water falls, it's converting gravitational potential energy into kinetic energy. So it's speeding up for that reason. So if that water is getting faster as it falls, if the speed is going up, then according to our continuity equation, the cross-sectional area of that stream has to be going down. So you can see it here where the cross-section of the stream is wider here than it is down there. And that's true even though this stream is not contained in a pipe, the continuity equation still holds. That narrowing indicates that the speed is increasing. We've got this inverse proportionality between cross-sectional area and speed. So in general, when we have a fluid moving through a wide section of pipe, we expect it to be going slow. And then as it passes into a narrower section of pipe, we expect it to be going fast. But to make that happen, to accelerate our water here, we need to be able to explain that using Newton's laws of dynamics, explain that using forces. So let's picture now here that in this wide section of pipe coming in from the left, we've got water moving slow, but at some constant slow speed. So no acceleration, net force is zero. This water is in dynamic equilibrium. Dynamic equilibrium in this zone. But then as the fluid approaches the section where the pipe is narrowing, we must have an acceleration zone here where the speed is changing from this slower speed to this higher speed. So we must have a net acceleration to the right in this zone, which must come from a net force to the right in this zone. But then past that zone, once we're in the narrower section of pipe here, the water is back to dynamic equilibrium, but now at a higher speed, going fast over here. So back to dynamic equilibrium on the other side of that acceleration zone. So let's examine now what's happening in that acceleration zone where the pipe is narrowing. What is the mechanism that is causing the water to speed up as it moves into the narrower section of pipe? So picture here a fluid element. Here is one in blue, this sort of a coin-shaped section of water over here, initially moving slow, and a free body diagram for that fluid element. Ignoring gravity here, supposing everything is just moving horizontally, then the forces on this fluid element are going to come from the pressure in the fluid surrounding it. So point one is the fluid behind that fluid element, which will be pushing with its pressure force to the right. Then point two is the fluid in front of that fluid element with its pressure pushing back on that fluid element to the left. And so here we've got the, let's see, oh, do I have these mislabeled? Let's fix that. Our free body diagram is going to show a force from the pressure of fluid 2, the pressure in front of it pushing to the left, and then the force of pressure from fluid 1, the fluid behind it pushing it to the right. And those two pressure forces are going to be balanced if the net force is 0, if we're in dynamic equilibrium. Okay, then we enter the acceleration zone here where this fluid element in blue gets squeezed. And then by the time it's over here in this zone, that same fluid element has been squeezed from this coin shape into this rod shape here. But we're imagining that if it's an incompressible fluid, that the volume of this coin-shaped bit is equal to the volume of this rod. The volume of it doesn't change, it just changes shape as we squeeze it into the narrower section of pipe. So over here, back in dynamic equilibrium, moving fast now, this fluid element is feeling a pressure force from the fluid in front of it. That's 0.6 pushing back on this fluid to the left, and then the fluid behind it at 5 is pushing to the right on this fluid. That's the force from pressure 5. And those are, again, our balance. This is dynamic equilibrium, again, over here. But in order to speed up here in the acceleration zone, this is what must be going on. It must be the case that the fluid at 3 must have a higher pressure than the fluid at 4. So that the fluid at 3 is exerting a rightward force due to pressure than the fluid at 4, which is exerting a smaller leftward force due to pressure. We must have a net force to the right. Therefore, the pressure at 3 must be higher than the pressure at 4. And we could sketch this graph. A graph showing the pressure in the pipe as a function of horizontal location, x. We sort of lay out an x-axis along the pipe, passing through points 1, 2, 3, 4, 5, and 6. So at points 1 and 2, this is in the wide section of pipe. We initially have some high pressure in that wide section of pipe where we are in dynamic equilibrium. It's the same pressure at 1 and at 2. But then the pressure at 3 has to be greater than the pressure at 4. So our acceleration zone is marked by a drop in pressure. This pressure gradient right here, a gradient means a change over distance. A pressure gradient, that's causing our net pressure force, with the pressure at 3 being higher than the pressure at 4. So the slope here of this pressure versus position graph, the slope is going to be related to the net force that we get that's causing acceleration. And then beyond that location, into the narrower section of pipe, we're back into dynamic equilibrium, where the pressure at 5 is the same as the pressure at 6, but note that now it is a lower pressure than it was back at 1 and 2. So the pressure being high or low doesn't necessarily cause any acceleration. It's the pressure changing, a difference in pressure, the pressure behind the fluid being greater than the pressure in front of it. That's what's causing the acceleration there. And so we generally call this effect where a fluid speeds up as it moves through a narrower section of pipe, the Bernoulli effect. And it's related to the pressure being higher here in the wider, slow-moving section, that capital H is for high pressure, then our pressure being lower over there in the narrower, fast-moving section of pipe. High pressure, low pressure related to the fluid speed, the Bernoulli effect. Note here that the fluid is moving faster where the streamlines are closer together. The compression of those streamlines here is a visual indication that this fluid is moving faster here. So that's a way to interpret what you're seeing when you look at a diagram of streamlines. The closer spacing indicates the fluid going faster. All right, so let's look at an application of this Bernoulli effect. Imagine that we've got here a hill, and the yellow is just the air above the hill. And this is on a day before the wind starts to blow. But then here the wind starts to blow to the right. So with the wind blowing to the right, what's going to happen is at first the air blowing this way is going to like run into that hill and sort of pile up at this hill here. And that pile up of air crashing into this hill that's blocking its way forward is going to cause an increase in pressure here. Pressure is going to build up here as air crashes into this hill. On the far side of the hill, air is vacating this region and moving off to the right, causing a low pressure zone there, where where the air that's leaving is not being replaced. Now, okay, we're not in a steady state flow yet because we're getting these buildups of pressure here and a decrease in pressure over there. So what happens next is that this high pressure zone, that high pressure is going to be pushing back on the incoming air, and this low pressure zone is going to be pulling back on the outgoing air. And we're going to get a net effect near the top of the hill where this high pressure is sort of pushing air up over the top of the hill, and this low pressure is pulling air down the lee side of that hill, and we're going to get an acceleration here, an acceleration from high pressure to low pressure. The net force on some air here is going to be around this direction, high pressure pushing this way, and the low pressure pulling that way. So an acceleration around the top of the hill like so. And we're still not in steady state. We've got to establish some streamlines here. So the next thing that's going to happen, well, it helps to imagine now some streamlines where the air coming in from the right then follows a streamline that is pushed up by this higher pressure zone over the top of the hill and then drops down into this lower pressure zone, so that over here we've reestablished the streamlines that we started with back on the left. But in between, they get squeezed here. And there's no pipe containing this air, but we can still imagine the pipe analogy here and imagine some gate 1, that a bunch of the air passes through. These 3 streamlines pass through gate 1, and then those same 3 streamlines pass also here through gate 2, just above the peak of the hill, as if it was a pipe like this, as if it was a pipe. And our Bernoulli effect has that we'll have a higher pressure here where the pipe is wide and the air is more slow moving, lower pressure here where that pipe is effectively narrow and the air is fast moving, and then back to high pressure over here as the pipe widens out again. The continuity equation says that the flow rate at gate 1 has to match the flow rate at gate 2. So AV at 1 equals AV at 2. And since the gate is narrower at 2 than at 1, the small area means the big speed. So our speed at gate 2 is greater than the speed at gate 1. So our air has to speed up as it goes over the hilltop. Part of the reason that we often get very high winds on the tops of mountains. High winds is that air has to speed up moving over that peak to get past it to the other side. And we've seen that what causes these speed ups are pressure differences. So we can also conclude that the pressure here at gate 2 must be lower than the pressure at gate 1. So we get a low pressure zone where the air is moving fast over the top of that hill. And now we've got our eventual steady state flow will be established like this, where we have a low pressure zone at the top of the hill where the fluid moves fast. And we can make another comparison here to aerodynamic lift on a cambered airfoil. That would be a cross section of an airplane wing. So let's say this is an airplane wing here, and our plane would be flying to the left in this picture. So we can imagine the air moving to the right over this wing. And with our wing being flat at the bottom, but sort of curved in a hill-like fashion at the top, that's going to force the incoming air to move up over this curve, like moving up over a hilltop, which is going to create a low pressure zone here above the wing where the air is curved. Compare that to the air below the wing, where it's flat down there. That air is not deflected at all. That air doesn't have to move off of its original path. And so the air pressure below the wing stays relatively high compared to the air pressure above the wing, where the air pressure drops. And then if you look at the pressure forces on that wing, with high pressure below pushing up on the wing, but a lower pressure above pushing down on the wing, the net pressure force is going to be upward on this wing in this circumstance, giving us an upward lift force to help keep the plane aloft. So there is how we can get aerodynamic lift from this Bernoulli effect from the continuity equation. I should note that there are other effects that also contribute to lift, not just the Bernoulli effect.